Hi, in this video, we're going to take a look at model-based clustering. All right, so the big idea with model-based clustering is that we believe that we have several different distributions are coming together, and that's what we're seeing in our data. So from like a clustering point of view, a cluster corresponds to a different density, probability density. So the vast majority of these implementations are for the multivariate normal distribution. So if you don't remember the multivariate normal distribution, go ahead and check that out. That's important. You're going to need to understand it for this one. So when I talk about multivariate normal, so the parameters for those are going to be the center, or like the mean of it, and the covariance matrices. Those two things determine all the properties of a multivariate normal distribution. All right, what we want to do, we're going to take our data, we're going to assume that we have some kind of distribution. Now, how specifically we want to be, it will depend on what we understand about the data beforehand, and then we're going to run our model to find the best clustering, the best densities for our data. All right, so the big concept here is that clusters correspond to different probability densities. My dog is barking. My dog wants in. Hopefully a member of my family will be so kind to get the dog while I make this video. All right, so in general, the more data I have, the fewer assumptions we need to make regarding my data. So if I have very little data, I usually have to make bigger assumptions to be able to reach some kind of conclusions. If I have a whole bunch of data, I really don't need assumptions because of the idea of convergence. I pretty much just see what it is anyway, close enough. I don't really need to assume any particular properties. So when I go through this, I always need to do kind of like a smell check. Does this sound reasonable for the situation I'm in, for where my data is coming from? Now, a nice feature about model-based clustering is that if I want to take like a Bayesian point of view, I can incorporate prior knowledge. I can have a prior distribution. We're not going to talk about that because I feel like priors really don't fit a data mining approach so much. But if you want to get into it, go ahead and look at the mclust package in R and start looking at it. I think it's interesting, but for like a data mining point of view, we usually don't do too much with priors. Another nice feature about model-based clustering is that it'll pick out how many clusters it believes that there are. So it'll figure out the number of densities for us. So remember that when we do the partition techniques that we've been previously talking about, like k-means and partition around the medoids, there we have to have some kind of idea of how many clusters there are supposed to be. With model-based clustering, we don't need to know beforehand. So that's really nice. We can just drop it in and it'll spit it out for us. All right, so I'm going to go through and we're going to look at the Geyser data set from the mass package. Looking through this looked like the best fitting data set I could find through my internet research for multivariate normal. So I went ahead and grabbed this. So the first thing I want to do, I want to get an idea of what I've got. So what we're going to do, I'm going to go ahead. This data set only has two variables. It has wait time and duration. So what we're going to do, we're going to plot these, and then we're going to do a contour plot. The contour plot is very similar to like when you look at a map. The contours indicate your z-axis, how much elevation you have. So we can drop this into R, and I'll spit this out for us. And if you've taken Calc 3, you're going to be familiar with these. All right, so what this is showing is that you see I have a little hill here, I have a hill here, and I have a hill here. So look at kind of the ellipse-like shape going along here. All right, what this is saying is that all of these points that are in this ellipse are relatively near each other in their height on the density estimate. All right, so we have wait time on the x-axis, we have duration on the y-axis, and what this is saying is that these points that are here are higher up than the points that are between these two contour plots or contour lines. And then if I go down a little bit, all the points I've looked at previously are higher up than the points over here that are between these two contour lines. If I go a little bit down, I'm going a little bit lower on the height aspect. So if I follow this line along on the contour plot, this is saying that along this plot, the density is the same height for all of these. And how you want to kind of envision these is that this is like a mountain, and this is the peak of the mountain, and we're going downhill as we move this way. This is a peak of a mountain, and it's going downhill as we move this way. Over here, we've got two peaks of a mountain to two peaks of mountains. That means that we've got a saddle in between. So it's like, if I go this way, we're going downhill, we get down to a saddle, and then we go back uphill. Over here, we have another hill. If I go this way along the hill, I'm going downhill. If I'm going this way along the hill, I'm going downhill. If I'm going this way along the hill, I'm going downhill. Here, we have another saddle. So if I was standing on this hill, I started walking, I'd be going downhill, get to the saddle, and then I'd go uphill on this part. And we want to kind of envision this the same way we do when we do like orientation or land navigation for those of us who have worked with a map and compass before. If you haven't, well, just kind of ignore what I just said. All right, so I'm looking at this, and where are we going? I'm getting the impression that there are probably 3 densities for the data, 1, 2, and 3. I'm getting the feel that I've got, this is the center of one multivariate normal distribution. This is the center of another multivariate normal, and this is the center of a third. So let's go ahead and do model-based clustering, where I'm going to say there's 3. Now, something you'll notice about this, when I make this declaration, I have not said what the centers of the distribution are. I haven't said what the covariance matrices are. Kind of an interesting aspect to it is I'm just saying, hey, there's 3. Go figure it out. Go figure it out. All right, now when I run it, I get, it gives me some output. So model name is going to come up later. So this corresponds to the assumptions of the model. And then BIC is the Bayesian information criterion. And the log likelihood is for the maximum likelihood estimate. And we're using the EM algorithm for those of you who have taken stat theory. Good stuff, good stuff. All right, so when it's all done, it says it's multivariate normal. It is a finite mixture model fitted with the EM algorithm, and it's saying it's an EEI. All right, so this is saying that we've got diagonals and equal volume and shape. The main thing is that we've got equal volume and shape for all 3 of these sub-normal distributions. So this model is assuming that whenever I look at my ellipses corresponding to the multivariate normal, is that the ellipses have equal volume and equal shape. Kind of a big assumptions. And that we've got 3 subpopulations going on. So here's our log likelihood estimate. Number of data points, our degrees of freedom. So remember that when I do these calculations, I'm making assumptions along the way. The more specific the assumptions are, the fewer parameters I have to be estimating. And so when we do this BIC, we're trying to find the sweet spot between number of parameters and best fit. The more parameters I have, the more I can overfit. I don't want to overfit. That's why we call it overfit. So the BIC kind of gives me an idea of what is a good way to go. And so here we've got 3 different distributions, and it's saying there's 91 points correspond to the first one, 107 in the second density, and the third has 101 points coming from that density. All right, let's take a look at this, see if this seems reasonable. So remember, it said EEI is the best fitting distribution. Let's take a plot. So it's going to plot the BIC for each of these. Now, what's going on here is if I had more, if I tried a whole bunch of different number of clusters, then it would have a bunch of line plots for the number of clusters. Here, since we said there's 3, it's just giving me 3, so I can see that the EE or the EII, the VII, and I guess it would have to be EII. These are all kind of like, you know, plotted down here. Since they're overlapping, it's hard to see what's going on. If we want to, we can extract it manually. All right, so now let's go ahead and plot the classification for each one. All right, so here we've got a density, and a density. Now, something that's kind of jumping out at me is that this kind of has a different shape out here. You know, it's kind of an unusual pattern. And I've got a lot of points here. So I'm kind of worried that maybe there might be something going on in the middle here. Don't know. Let's keep going. All right, now next one's going to look at uncertainty. What this is going to do is it's going to give me an idea of how confident the model is for each individual point. So I can see that if it's a very, very, very tiny point, I have a high level of certainty that that point is with the correct distribution. So this is under the assumption that we have the correct 3. Remember, in multivariate normal, it goes out to positive or negative infinity in every single direction. That means that potentially I could have a red point all the way up here. Potentially, I could have a green point all the way here. I have a blue. Potentially, you could have a point anywhere for any of the densities. But what this is doing, this is finding the one that corresponds to being the most likely under the assumptions. So here, when I look at these points, I can see, well, the model's not so sure that this is the correct density to be corresponding to. We can see with these blue-greens, it's not really confident that these blue-green points, the bigger ones, are labeled with the correct density. It's very confident with these, but not so much with these. Now here it goes ahead and it plots the densities for us in a contour plot. And we can see that these have very similar shape and orientation. All right, so what we've done, we let the system just kind of go ahead and pick the model for us. All we did was just say the number of densities. Well, what options are available? Let's say I know a priori that it should have a specific feature to the model. Well, then I can tell it to only look at those types of models instead of going through all those other ones that were plotted in the BIC plot. All right, so in the MCLUS package, it gives us a way of extracting all the different types of models and their corresponding names. So here, this is what we call the parameter when I run the MCLUS function. And here's what it corresponds to. So the EII here is spherical. So not any ellipse, it's going to be, you know, circular. And then we're saying equal volume. Here we're saying spherical, but varying volume. So here, this is going to have more parameters. It's going to be more flexible and have more parameters than the EII. Next, we're saying diagonal. That corresponds to the covariance, equal volume, and equal shape. So diagonal is talking about covariance again and equal shape. Diagonal, equal volume, varying shape. Diagonal, varying volume, and shape. Here we're saying we've got ellipsoids, but they have equal volume, shape, and orientation. So now we're allowing them to be different shapes, but the ellipsoids, one could be like really narrow, another one could be more circular, but they have to have the same volume to them. Now here we're going ellipsoidal, equal volume, and orientation, but the shape can vary. That's kind of interesting. And we can just go through, read them all off. And when we get all the way down here, we're saying that we've got maximum flexibility on what's going on. So in general, roughly speaking, this is 100% correct, but we can see that there's kind of like systematically it goes from more assumptions to fewer assumptions. And if I have a lot of data, I'm going to be going with the ellipsoidal varying volume, shape, and orientation, because if I have a crap ton of data, it's going to converge on a more precise version, like pretty closely, if the more precise version is actually the correct model. And so I can take a look at the output and go, hey, maybe it looks better up here, and work through it. But if I have very little data, I'm going to have to make a lot of assumptions about what's going on. Right now, if I'm dealing with univariate data, so that's one dimension, I can go just, E and V, so we go equal and varying on the dispersion of the model. If I'm dealing with multivariate data where I have more observations than I have dimensions, then I can use any of the ones listed in the EM model names. So here are all the options that I can spit out, I can put into the model. Now, if I'm in a situation where I have less data than I have dimensions, then I'm limited to what I can go with. It has to be a spherical or a diagonal model. Now, this is one of those fun times in statistics where I can have fewer data points than I have dimensions. All right, that's good. That's very good. Now, also, if I'm in this type of situation where I have more dimensions than I have data points, I probably want to pull in a conjugate prior. So use some prior knowledge, some prior information to get things to work out better if I can pull off getting that information. All right, so now what I want to do, I want to go through, I want to dig into each of the different models and see, hey, do each of these look all right for my data set? So what we're going to do is I'm going to make a list of MCLUST models, and I'm just going to iterate over all of the different possibilities. Iterate over all 14 of these. So the data is my geyser data. The model name is just the value that I have up here. And then we're going to go ahead and plot the classification just to see, hey, does this model look good? And then I slap on a title on there that includes the parameter of the model. That way, if I want to go back and start digging into it, I know which one to look at. All right, so if we say it's EII, then we can see that they're all parallel. They've all got like an equal shape to them. But there's a bunch of them. It's kind of a weird setup. I mean, look at the gap here to the gap here. I'm not feeling it. I'm not feeling it. I don't think this is a good choice. Let's move down. I mean, a bunch of points here, a bunch of points here. I mean, I really wouldn't expect to see this in with a normal distribution. So I don't think the VII is a good one. All right, next we got EEI. All right, I mean, that's pretty consistent to what we've already been looking at. Now we've got VEI. Huh, what's this? We've got green, blue, red, purple. So this is saying that if this is the correct model, that there are actually 4 distributions going on. That kind of jumped out. I mean, I wasn't expecting that when I was building this up. Let's keep going. All right, so now we've got EVI, green, blue, red, purple. So once again, it's saying 4 distributions. And these kind of fit all right. I mean, you can kind of see these guys, the purple fitting together. Let's keep on going. Once again, I've got 4. Huh. Back to 3 again. 4 for Eve. Okay, now here we've got 1, 2, 3, 4, 5, 6. So let's take a look. Some points here, some points here, bunch of points there. Maybe, but I'm kind of not really. I'm not really. Maybe possibly if I had more data, it might show up. But you know, to be parsimonious, I'm gonna shy away from using this one. Once again, 4. Back to 3. Okay, okay. Oh, hey, this one's very different. All right, so let's start looking at this. So we've got 1, 2, 3, 4, 5, 6. Now, something that's jumping out at me is that these are overlapping with each other. One thing I want to see when I have a plot like this, I want these to be separate, distinct, different ellipses. I don't want them to overlap on each other. So I don't think this is right. I mean, possibly this would be the correct shape, but I would want to say that these two would have to be together. So 1, 2, 3, 4, 5 is probably a better fit. But let's take a look at it. If this is, you know, just look at my different densities. It's kind of stretched out here coming from the green. You know, it's, I mean, I'm mainly just what's jumping out at me is the shape of this. I've got overlap with the blue and the red. I'm really not feeling this one. All right, so back to 4. Back to 4. All right, so at this point, I mean, there's been so many of them that they all looked like they looked pretty good if I went with 4 instead of 3. So what I'm going to do, I'm going to say, hey, you know what? I think that there's 4 at this point. I have changed my mind. I have updated my opinion. So let's go ahead and run this with 4 distinct multivariate normal distributions, and let's see what we get. So what I do, I set G equal to 4, and what this is going to do, this is going to go through all of those different model like shapes, the ellipsoids, the sphericals, varying volume, and you know, same volume, stuff like that, and it's going to try and find the best one. So here we have a VVI. All right, what is VVI? It is diagonal. So diagonal, it refers to the covariance matrix, varying volume and shape. So it's letting the volume and the shape vary, but the diagonals are all, we're talking about diagonal covariance matrices. That means that the X and Y directions are going to be independent of each other. Here's my log likelihood. How does this compare to the previous one? So my log likelihood is 1330. 1330 compared to 1371. I mean, I'm pretty close on the scale. And here we've got negative 7,800, which isn't too far off from what we have over here. Scrolling down. Pretty close on, you know, considering the magnitude of the values. So I feel like 4 is the correct model. I feel like this is a good one to go with. So diagonal, varying volume, and shape. Let's go ahead and plot it. Let's see what it looks like. Let's look at the classification. And here, I mean, we've pretty much already seen this anyway. Notice how fat this is. This is pretty spread out. So this is saying that this is a high variance distribution. And notice that because these are diagonal distributions, the ellipses are going parallel to the axes. So the major axis is parallel to the x-axis. The minor axis is parallel to the y-axis. So I don't have any tilting. I don't have any rotation of the ellipses. Let's take a look at the uncertainty. All right, so here we can see that it's not really certain about these points. Not 100% certain about these points or these ones. Now let's take a look at the density of each of these subpopulations. All right, so what's going on here? You'll notice that there's only 3 that are plotted. What's happening is that the one that's here has so much variance to it that the height is below the threshold for plotting, and that's why it's not appearing. So there's 1, 2, 3. There's actually a 4th one here, but it's so low that it's going to be below, the peak is actually below 0.005 because it's such a spread out distribution. And as an added bonus, as a cherry on top, we've got the ability to get a dendrogram, just like we have for the H-class function. And so let's go ahead and do that. I went ahead and just went with a VVV when I was doing this. We could change that later. This only takes certain model types. So let's go ahead and make the dendrogram and plot it. And so here we can kind of get a feel for what our model looks like, or the combinations. And so if I want 4 clusters, let's see here, if I cut here, that's 3. I cut here, I'll get 4. So, you know, now something about is the height, so when you see that a range of values, a height range that gives you like more flexibility in slicing to get a certain number of clusters, that makes you more confident in that particular number of clusters. Here with 4, I mean, it's kind of it's not far off. 4 and 5, there's not much of a distinct difference, but there is kind of a difference between 4 and 3. So maybe 3 might be the right one. I don't know. We would have to keep going and check it out. All right, well, that's all I got for you. I hope you're staying healthy, have fun, and take this and apply this to your data, and go through, look at some priors, do some other stuff, and take care.